durch 0 dividiert für bestimmte Werte des Vektors x oder auch von hier könnten irgendwie Singularitäten kommen. Das ist tatsächlich richtig und wir müssen sicherstellen, dass zumindest in den Bereichen des Zustandsraums, wo sich unser System aufhalten wird, dass U nicht unendlich wird, dass also keine Singularitäten zum Tragen kommen. Wir wollen hier nicht in detailliertere Untersuchungen eingehen, sondern nur noch abschließend die Hinweise notieren. Das Ganze ist nur praktikabel, wenn keine Singularitäten im Regelgesetz zum Tragen kommen. Ich drücke das mal so schwammig aus, zum Tragen kommen. Es darf grundsätzlich schon sein, dass da Singularitäten möglich sind, aber in den Bereichen des Zustandsraums x1, x2 in dem Beispiel hier, die das System tatsächlich annehmen kann, dort darf eben keine Singularität wirksam werden. Das ist gemeint. So, jetzt wollen wir uns nochmal anschauen, wie denn das ist mit den Polen, die wir vorgeben können. Natürlich werden wir die Pole dieser Übertragungsfunktion in der linken komplexen Halbebene vorgeben und je weiter links wir die wählen, desto schneller wird die Dynamik des geregelten Systems sein. Das kennen wir schon, das können wir durch Vorgeben von Polen machen, dann gewinnen wir dadurch die Alphas und das Regelgesetz steht da. Allerdings können wir ja hier nur Delta-Pole vorgeben und nicht etwa n-Stück, wie wir das zum Beispiel bei der Ackermann-Formel ja gemacht hatten. Wir haben vorhin schon diskutiert, das Delta kann kleiner als n sein, es kann aber auch gleich n sein. Wenn Delta gleich n ist, dann gibt man hier offensichtlich so viele Pole vor, wie das System Dynamik hat, wie das System Freiheitsgrade im Zustandsvektor hat. Und dann nehmen wir mal an, dass wir damit auf der sicheren Seite sind. Aber wenn wir hier weniger als n Pole vorgeben, dann haben wir da kein so gutes Gefühl mehr dabei. Dann gibt es ja eine Zustandsraumdimension, in die wir offensichtlich nicht mit unseren Polen eingreifen. Und das Problem kennen wir von der linearen Entkopplungsregelung schon. Auch dort hatten wir ja Delta-Pole vorgegeben, die Systemordnung war aber n. Und tatsächlich passiert hier etwas Ähnliches wie bei der Entkopplungsregelung. Es kann sein, dass das geregelte System eine Nulldynamik hat, eine unbeobachtbare Dynamik, über deren Stabilität man nicht so leicht was aussagen kann. Im linearen Fall konnten wir über die Invarianten Nullstellen etwas aussagen, im nicht-linearen ist es komplizierter. Also würden wir notieren Folgendes: Bei Delta kleiner n, kann interne Instabilität auftreten, genau wie bei der Entkopplungsregelung. Also Vergleiche linearer linearer Entwurf. Dort hatten wir dann unbeobachtbare, instabile Eigenwerte bei der Entkopplungsregelung. Ein ähnlicher Fall kann hier auftreten. Ist aber Delta gleich n, bei Delta gleich n, Delta gleich n tritt das Problem nicht auf. In der Übung 9.1 wird dazu auch ein Beispiel angesehen und etwas näher darauf eingegangen. Okay, soweit die Ausgangslinearisierung. Hier ist nochmal das Regelgesetz und ich danke Ihnen für die Aufmerksamkeit.
You need to flatten the output. That is, if you save it, it asks you usually if you flatten or not, and please use the flatten option. The best way is really a week before, 1.5 weeks before, I put a test exam online and please test, because after uploading, you will see if you can read your solutions yourself. If your solutions don't appear in the 2M exam server, then you need to change the way you're saving. It's sure that the exam is online, yes. Well, it's not dependent on how many international students is already registered. I'm reading through your question. Sorry, I didn't know what it was reading that. We really have to decide at one point if it's online or a physical presence, and we decided it's an online exam, so it cannot be changed. Yes, so I'm reading now regarding homework 4. It is explained in the video that giving a more accurate initial value and initial variance rather than random can help for converging. I hope you can see it already in the slides. Let me just upload it now to the window. Computer is sleeping. I think. Just a second. Almost made the same mistake as before. Trying to open a window here in BBB. I was sitting in an empty room and nobody was there. And at one point, I decided it cannot be that everyone else but me is wrong. So I was in the wrong window. Let me just here. No. Okay. Public chat. I make myself. Second. I just downloaded it. You need to scroll to the right slide with this visual condition. 64. Right, it's following. Oh, it's here. You see basically the true value for the process I'm observing in case of explained in this tutorial was I'm observing something which should be the yellow line, but since I'm having very bad measurement system. There is a noise on top of the yellow line, and the noise results in measurements along the blue line. So the blue line is not really correct. It's just swinging. It's just, since Kalman filter has the assumption of a zero mean, the blue line will be swinging around the yellow line, and the amplitude, this would be basically kind of corresponding to the covariance or variance of the signal, tells me how good my sensor is. If I have a very small swinging, this means I have a very good sensor with very little noise. Then there will be just small deviations between the yellow and the blue line. If I have a bad sensor, then the swinging would be very large, like here. The sensor is giving a very bad output. And now, of course, the best way would be to let the filter start directly at the correct position. So instead of starting with 0, 0, 0, as is done here, I could have an initial guess bringing me closer to the solution. And this does not require the filter actually to correct over time to the correct value. So we see here in the first step at the beginning, there is a huge difference between the filter and the output. The filter is saying empty. It's not even going all the way to 0, and it should be 1. And the filter over time climbs to the correct position. And now, depending on your Q, depending on the assumed system model in your Kalman filter, if you have a small Q telling the system that the modeling of the state transition is correct, then the Q would be small. The filter would be trusting a lot its own response. The filter would climb here very, very slow. So you would see a very long time until the filter gets to the value. So if you have a system which has a very good modeling of what's happening in this over time, and you started with the wrong value, the filter will take quite a long time until it reaches the true value. So it's always a good idea actually to start with a good assumption of where you are. If you have a large Q, just because you assume from the very beginning that your filter is not really predicting well, then the filter would be climbing faster. But you would also see, as is shown later on the slides, that it would be more also tempted to follow the measurement instead of following its own predictions. So having small Qs, having a good modeling of the state, leads as a side effect to a long time until the filter really agrees with the measurement, just because the filter will be trusting its own prediction too much. That's why having a good small covariance in the measurement, of course, also helps the filter to converge. If you have a bad initial assumption and the covariance of the measurement is small, this would of course also lead to a faster lock-in on the correct value. I just lost now where I was. Yeah. What does A mean? How do homework 4, slide 9? What does A mean? Slide 9. The A is the state transition matrix. I'm pretty sure. Let me just see if it's too far. Well, this is basically taken from a little broader explanation. So what we don't worry about this continuous functions. So you can imagine that you can write the state transition basically as a continuous function with time as a parameter, which allows you basically to see the continuous evolution, what's happening over time. What we are talking about here is basically discrete Kalman filter. That means a filter which which predicts the states at discrete delta t time intervals. And let me just see if it's here. So A is basically the in this case this would be the continuous the change, and since it's a static model, there is no change. The A will be here in this case 0. So this slides unfortunately have a slightly different terminology to what I'm using in the other ones. Here F is our A. F is basically the discrete representation of the filter, and A is basically the continuous model. So what our A in the filter on all of the other slides are is here F, and it should be also here from the Kalman equation. Let me just see where they are. In the wrong direction. Okay, since F is equal to 1, it got omitted here. So the F would be showing up here in front of the X. I think on some other slides it will be a pure Euclidean equation. This is also what I meant. If you look for other explanations, sometimes different parameters are used. So I would really say for the exam, we use A as a state transition matrix, B as the control matrix in the prediction equation. We use R as a sensor noise. We use P as a state noise, and we use Q as a system error, basically the matrix I was just mentioning before, telling the filter how well the state representation matches what's happening in the world. But you see, like, there are many examples which are using slightly different notations. They mean the same thing, it's just a different letter. In the Kalman filter example, page 28, why is H a vector here? Let me see what 28 is. A week ago, so I've forgotten. You see, this is basically what I just meant. This is in our notation A, not F. Here it's F used. It's just from a different notation, but it's the same. Well, the H this is basically again same thing. H is here the measurement. The H is the measurement. The first parameter is the measurement, and the second parameter here is the covariance. So what we are usually writing is you can write it here. It will be right. So what we usually write is just no, why is it not writing? comma R. So what you see on the slides is usually something like this, or you could put it in square brackets. Here. Like this. So the first parameter is the measurement itself. It's a lowercase r, and this can be a vector. This is a vector. In a special case where you have just measurement, of course, the vector becomes a scalar because it's just one parameter. And the second parameter here is basically the covariance of the measurement. This is what I just meant. In our notation, it's R. It's basically the covariance of your measurement that you provide to the filter.
Sorry?
Yes?
So that was my question, and basically it comes from, so we have y, so the measurement is equals to h times x, right? Y is equals h times x.
Let me just see, because I'm... Maybe I'm explaining something. Why is basically the measurement in
yes, and that formula is y is equals h times x.
Yes.
So then the question is, y is a vector with dimension 2, and x is
because you know, this is the filling model. So basically, you have here. You as a measurement, they assume that you can measure you measure the filling and the velocity.
yeah, that's clear, but I mean for the matrix multiplication to make sense, H must be a 2 by 2 matrix to map from X, which is a 2 by 1 vector, to Y, which also is a 2 by 1 vector.
Yeah. How is the state represented here? So, sorry, I just tried to. The state is X and the filling rate. Yeah, so yeah, it should be actually a matrix, not a vector. You're right.
So then my guess would be that it would be 1, 0, 0, 0 as the matrix.
It would be 1, 0, 0, 0. Yes, because
okay.
it provides just it maps basically. No, it would be 1, 0, 0, 1 because the Y does not provide. We will see it with data associations when we do. Was that data association already in the? I think SLAM was already on the slide. Did you see already SLAM in the video?
I don't think so.
Okay, so this will actually become now clear in the next lecture. I thought I put it already online. So basically, what you're saying is correct. Z basically is not R, it's Z. Z is the measurement. No, is equal to H X. And your Z can be, let's say X is a two-dimensional vector. Let's assume for simplicity that X and Z are in the same coordinate system. So you have two parameters in the state, and you have two parameters here in the measurement possible. But now you have two sensors which provide the measurements. The sensor 1, which provides a Z1, is measuring just X, and it's not having, so if it's not providing the second input, And Z2 is doing the opposite. It's measuring just Y and not providing X. So when I update my filter with Z1, then my H matrix, for the case that I'm providing the Z1, is just 1, 0, 0, 0. And the H2, if I provide measurement from just the Y parameter, would be 0, 0, 0, 1. And this is something which will show up now in the next lecture when we apply this to SLAM, to simultaneous localization and mapping. Just because our state representation will be not only the position of the robot, but the state representation will be also the position of all surrounding landmarks which we're using for navigation. And in this case, some of the landmarks may be not observed at the current step, and this is exactly represented in the H function. The H function tells basically which parameters of X correspond to the current Z observation.
Okay. And here, because we only have Y, right? The other one is 0. It should be 1, 0, 0, 0.
It's 1, 0, 0, 0. So basically, basically just check it with the next set of slides. SLAM is basically we do, one of the reasons why we do Kalman filter is not only to filter our own position, but you can use Kalman filter also for mapping, SLAM, simultaneous localization and mapping, and you will see in the slides that this is just really extending the vector. So the X of my state representation, there is no secret I'm telling here, it would be the robot. This is basically a vector representing X, Y, maybe also velocities, maybe also accelerations of the robot. And the state will be extended to also landmarks, landmark 1, all the way to landmark N. So now the filter will be not only updating the position of the robot, but at the same time will also track positions of the surrounding landmarks in some global coordinate frame. And as I mentioned before, you may have 100 landmarks in your state, so the state representation will be very long. It would be really just 100 L entries, and each of them will have at least 2 parameters, I assume. So it would be 200 parameters following the robot state. And in each step, of course, I will be updating the robot position because this is something I can always observe. But some of the landmarks in your map, the map is really, in this case, the state of the Kalman filter. Some of the landmarks in the map may be occluded, so maybe not visible. And in this case, basically the corresponding H entry will become 0, telling the filter that there is no coupling between what's in the filter and what I currently observe.
Okay, cool. Thank you. But generally, just another short question, but it's a normal matrix multiplication, right? It's not element-wise, it's a matrix multiplication.
It is a real normal matrix multiplication. So basically it's, and this is the problem also with standard Kalman filter, that H is really just a matrix.
Okay, cool.
But you will see later, extended Kalman filter will loosen this assumption. In extended Kalman filter, we will have the case that Z vector is just an H function from X. No? And you will see that this is there are very few examples where this relation is linear. In most cases in the real world, you will have nonlinear relations. That's why you need the extension to extended Kalman filter, which will come next. So we need to extend it to the map, and then you will see also how to drop the constraint that the measurement needs to be linearly dependent to the state. And the second constraint which we need to drop is that the next state, it's funny to draw it like this, that the prediction of the next state is also just a linear relation of the previous step. So what we have in the Kalman filter is this A matrix, which is basically giving us a linear relation between previous step and next step. This is usually, in most cases on the robot, you will have a nonlinear relation because, for example, your XY position may change depending on the current orientation. So suddenly you would start seeing a sine cosine expression of one of the state parameters in the matrix, and this is not allowed for linear transformations. I cannot have nonlinear functions as multipliers of parameters. That's why we will also need to extend this as well to a function f. I cannot write today, sorry, of x. So the next state is a nonlinear function f of x comes next. But you're right, this is actually a little bit unfortunate notation here. It should be a clear matrix. Pretty sure. Yeah, so this is always h times x. So the equation you need to remember for Kalman filter is the prediction equation. Prediction equations are two. The first one is that x, basically we usually put a minus. So the minus here on the top means predicted. The predicted state in the next step is the state transition matrix A multiplied with the previous step, really matrix multiplication. What can come here additionally is plus B times U if you know the control values. We talked about this earlier. If you have an external observer, you don't know the control values. So in most cases, you will have just this part because U is 0. The second equation you need to remember, just trying to see if I can find them here instead of writing. Unfortunately not. I will just write it as a text because this pencil writing. This is also something which will be your problem in the exam. If you write with a mouse, you will end up what I'm doing now. So the covariance in the next step, I just do minus like this because I cannot. The minus should be actually on the top. This is the predicted covariance. And the next step is A, P, A. The transpose should be also lifted. So this is A, P, A transpose plus Q. So this and this are the two equations for the prediction step you need to remember from the Kalman filter. This is basically how I predict the next state, and this is how I predict the next covariance. And for update, I need to remember the Kalman gain. Well, of course, now you don't need to remember. I just realized that you have the advantage that you have open book. In the previous exams, you had to remember it. So the Kalman gain matrix is basically P, H, other. And this inverse, this should be also lifted. So something like this, the covariance, predicted covariance times the measurement matrix. And this is basically, this should be inverse. this should be, if it's a scalar value, this is how I remember it. Just really from the way it's derived, it should be just really P divided by P plus R. So this was the way we were deriving the Kalman gain. The problem we are having here is, of course, that P and R can be in two different spaces. As we see on the previous slide, H is basically a transformation matrix transforming from the state space to the measurement space. And in general way, we have to use these H's here to transform the covariance of the state into the measurement covariance. That's why instead of having this simple P plus R, I'm having here this H plus PH transpose. It's just to project the covariance into the state of the measurement. The division here is replaced by the inverse, and here it's just because I need to. I think there is a transpose here as well. Sorry, I'm running it now from memory. So there should be a transpose also here at the H. Look at the slides. It tells you the correct equation. This is also just due to the fact that after dividing here, I'm still now in measurement space, and I need to convert it back into a state space. So this is basically something which I need for Kalman, and then a very important question is basically how do I get the new state? It's basically the predicted Kalman here. So basically, the predicted value gets corrected. This is not Y, but Z, sorry, Z. The measurement minus prediction of the measurement. So this is basically just telling me, it could be the other way around. This is basically, I have a system. The prediction is telling me I am here. This would be my X minus my measurement is telling me you are here. And the Z minus HX is basically just the distance between what the prediction is telling me and what the state is telling me. So this difference is basically just the change between prediction and measurement. And now the Kalman gain is just telling me whom do I trust more? Where do I put the result? Do I put it closer to the measurement? That means I have a K which goes towards 1. And or do I put it closer to my prediction? This means K goes towards 0. And which way K goes was explained, I hope, in the video. It really depends on the covariance of my state and the covariance of my measurement. So, and there is the last equation, which is basically the update of the covariance. It's basically identity minus K times the prediction of the covariance. So this is basically, these are just the equations you need to remember for the Kalman filter. Of course, now you can also just look them up in site. But you really need, once you understand, I hope, what's happening here, it's also very easy to follow how SLAM works and how all the other systems are developing. Let's just see. Okay, you're still talking about the age.
Hello, Professor.
Yes.
I have also one question about state variance matrix. Could you please explain the meaning of the function of this matrix P? Why the estimate value can better follow the measurement value when we increase the value of?
Are we talking about the Q?
Yeah, sorry, about Q. Yeah,
the one which
I didn't understand.
You mean the one which shows up here in the equation on top here?
Yes.
Okay, let me just try to find an empty. I tried to explain it already last time, I guess. Yeah. Here is a lot. Here's a lot of free space. I think it's easiest explained if you have just a simple system. So let's. I know what's happening. The computer is still broadcasting something here. I need to stop to kill a few tabs here because. I hope it will. Now it's faster. My computer was doing too many jobs at the same time here. It's basically, this is my one-dimensional space. My robot is somewhere here. This is my XK XK. This is where I was before. And now the robot is moving. And it moved in xk plus 1 to this position. This would be the correct xk plus 1. This is where the robot is in the next step. One is reversed. Okay. Now I can choose for my system different state representations. The easiest one would be really just to say xk state. So this is actually a vector. Right? This is my state vector. And this is just a position. So xk could be in simplest case just the position x. So this would be the simplest representation of the state of my robot. It's just representing its position x along this one-dimensional axis. Now, if I have a simple filter like this, of course, the only thing the filter can predict is that it will be at the same position again in the next step, because my A will be also one-dimensional matrix 1. So xk multiplied with 1 will be xk plus 1 predicted. So the prediction of this filter would be, I guess I am here. I'm trying to do it dashed. So this would be the prediction of this first filter. And you see there is a huge difference between the prediction and what the filter should be. And now the robot, of course, will make a different motions. So sometimes it will jump here, sometimes it will jump here. It really depends on the dynamic change, how the dynamics of the robot is. It will have a variance here between what the system predicts and what it should be. And this variance is exactly the Q. So Q is telling us basically what is the change, what is the difference between, what's the expected error between what my system predicts and what's actually happening in the world. So this would be a very big Q. Now a second possibility for my X, I did could be just to have xk. I try to do it in a different color. Now it's writes also better because my computer is not doing 50,000 jobs. Next, I could have the position. It's supposed to be dot. And the velocity. So I picked now a better model for my dynamics, which tells the system that there is a position and there is also a change of the position. And you can imagine if I run this filter, then the system, the prediction of, it should be dashed, the prediction of the filter will be not the same position, but now would also take into account the current velocity and would be bringing the prediction closer to where it actually should be, just because it has a better model of what's happening. Since my filter does not know anything about accelerations, it may still make an error just because during this time step, the velocity may have changed. So I could have a system which is currently accelerating, and I would be predicting just based on what I measured here. So the velocity over this step was possibly not constant, which would result also in an error. Just to make it clear, it could be also that it's slowing down. So basically the filter could also end up predicting here and the true value could be on this side. Just for convenience, I'm drawing it always on the left side. Of course, the filter could just overshoot just because the system is slowing down. So you see that not having a complete state representation would simplify my Kalman calculation because I have now just 2x2 matrices. And of course, usually I have more than just one parameter. So I just reduce the number of parameters in my filter. But at the same time, extending the parameter number is reducing the remaining covariance between the predictions and the true what's happening in the world. So that you see that the Q for the orange one will be a lot smaller because the covariance will be already a little bit smaller. You can imagine now if I add here acceleration to my filter, then the prediction will be even better because now I will have also, I could also take into account accelerations in the system. Of course, what I still don't take into account is changes of acceleration. So you could really go crazy, like how many derivatives you end up here. At one point, it doesn't make sense. But adding, for example, also the acceleration could bring me, for example, very close to in true position because I'm also the filter understands that there is some parameter allowing me also to change the value of the second one, and my Q will be very small. So basically, having a filter with many parameters with good modeling of my state allows me to bring to create a small Q value. The Q here will be large if I take just X, will be already a little bit smaller if I take X and X dot, and will be even smaller if I take X dot, X2 dot as my state representation. And since my filter understands the physics of my world, the filter will also start trusting its own prediction more. Just because if the previous, I need to draw it here, that's why I switch the slides. Let's say I had in the previous state some really good estimate of my position. Sorry, this is this one. This is the P of the previous step. And now I have a filter which has a very good model of the. So this part of the equation is just transforming the same thing. So without the Q, the two Gaussians would have the same sigma. So if I would not have Q, if I would have an ideal state representation, which is not making any errors, then the sigma would stay the same. So that means, since I know exactly what's happening in the dynamic case, I don't need to flatten it. But now, depending on the Q, the curve is flattening. So for the first case, let me just use green, I think, here's green. If I have just position in my state representation before, then adding the Q would be very large, would flatten the Gauss to something very flat. And this is exactly the variance between you see, in the green case, I will have a lot of discrepancies between what the filter predicts and where I actually am. And this is represented now by a large Q, which flattens the curve to really cover the possibility that I'm not really where I'm predicting, but I am maybe also somewhere else. If I am now having a beta filter, then I will start having a smaller Q, which flattens the Gauss a little bit less. And this is basically just, you see, this is just the variance of the difference between what the filter predicts and what's happening in the real world. I have a better system model, I have a better representation of the dynamic change. That means the error between what I predict and what's actually smaller. And for the acceleration, I would have even better this. So the filter will prevent the system to following too strong the sensor. So if the sensor is, of course, also ideal, and I think it's on the last slides also of this tutorial here. And here is, for example, this is the example where the filter is, where the tank is just being filled up with water. So it started with 0 and it's filling up. And now, depending on the Q, the system may follow more or less. I'm just looking because I think there is a slide for this. I just don't see it now here. It can. This is basically like if I have a Q which is very small, then you see the system will not follow the measurement, but will start trusting its own prediction just because there will be no large modification of the predicted covariance, which is just a transformation. So the predicted covariance without the model is just A. This is just the previous covariance projected into the new space. Without any errors, the covariance will be preserved. And now if I have a small Q, then the filter at one point will reduce his P to something very small and would not let a very erroneous measurement pull it away from it. So having a small Q is a desired property of the filter. And this comes back to the original answer about initial state being too far away. If you have a small q and you start with the wrong initial value, the system will trust its own prediction too long. And it would take it really a long time until the filter gets pulled by the sensor to the correct position. So starting with the wrong initial value is often a lazy convenience, but should be done, because you should try to have a small q, and you should trust your filter as much as possible.
Excuse me?
Yes?
I'd have another question regarding basically the P matrix. In our examples, P always converged, right? It always got better. Is there also the case that the P, so the state variance, might get worse over time?
Yes. Well, one example of P getting worse is if not the entire P, but some elements of the P may diverge. You know? And this would be for the case where you have an unobservable state parameter. So you could have made a mistake. You created some state, and now you provide measurements. And I advise you to always check the observability matrix to see if all state parameters are observable, if they can be observed by the current measurement. Many people don't do it. They just trust that whatever they measure is enough to keep it stable. And in this case, there could be an unobserved parameter, and then this corresponding diagonal element will suddenly start growing to infinity. So this will be one case where covariance will not converge. The second case is that you have a highly dynamic system. So you have a system which has a lot of accelerations. If I talk on the robot, there is someone which is changing the acceleration all the time. You know? And you used a state representation which models just the position, then the filter will not be able to follow, because you would need to choose a very big Q for such a matrix. Well, you know, in this case, it may also not diverge because the sensor will be keeping it, but it will get high values. So the wrong choice of the state representation, a too wrong modeling of the dynamics could result in large covariance values. And the last one, which is very important for really robotic for flying systems, this is what we have a problem on a drone when we were implementing it, is that if you have this will come now in the next slides when we go towards these nonlinear functions. What we will do is we will extend the Kalman filter to extended Kalman filter using linearizations. So we treat the system as a linear system just by using Jacobians around the current state. And this works fine, but there are cases where we have a highly dynamic system like a quadricopter, where the curvature of your function is so strong that the linearization makes a too big error. So, and I will show you on the board in a video what's happening there. In this case, you will notice that although you have correct measurements, you have a good representation of the state, the system will not converge, and this is due to the fact that this assumption of the linearization just doesn't hold anymore. This is basically something forcing people to switch from extended Kalman filter to uncentered Kalman filter, which will be also covered in the last step. So just basically, the first one was really your model is not sufficient. Sorry, the first one was your measurement is not sufficient. You don't measure, you don't observe all parameters. One of them is diverging. The second one is your state dynamics is not sufficiently represented. You have a lot of changing happening in the world, and you're using a very simple model for it. This will result in high P's. And the last one is the whole assumption for the Kalman filter is wrong. You need to switch to a different Kalman representation. Long story. Maybe we talk about these questions after we talked about extended and uncertain filter. Again, then you may understand maybe better what I'm talking about. But I hope
Thank you for your answer.
You get an idea. Mm-hmm.
Hello, Professor Boschka.
Yeah.
I have a question on the same topic of observability.
Yes.
Namely, suppose that I have a mobile robot.
Yes.
And I want to track its position. But the robot only has an accelerometer. Then, of course, the uncertainty in position will diverge.
Yes.
Now, suppose that I place markers on the ground, and the robot will recognize the markers and correct its position, but only if the robot is physically on the marker. So I can measure my location, but most of the time I can't. So is the system now considered observable or not observable?
The system is considered observable, but you will have a kind of a breathing covariance during the time. So you need to. This is also what happens when you have a camera and an IMU. IMU is providing you a lot of measurements, like 1,000 a second. And the camera is providing you maybe 10 a second. So every 1/10 of the second, you get basically also the position, from the camera. And every time in the Kalman step, you get an update about acceleration. So when you get the camera update, the covariance will shrink to whatever the camera precision was, and then it will start growing again until you step on the next marker and you shrink it again. Do you understand?
All right, thank you.
Yeah. So basically, since between the marker updates, the position is not observable, this filter will do exactly what I was just saying. Like the filter will just grow the covariance, and the reason for this divergence is the Q. The Q adds always some additional covariance in each step. And this is also why it's so important to have a good state transition representation, why your A should be correct. The better you model the A, the smaller will be the divergence between the updates while standing on a marker. Okay, das war zum Sonntag.
I have one question.
Yes.
How the assumption that the noise, if the assumption that the noise is not isn't Gaussian, is not satisfied, what would we perceive in the Kalman filter?
Kalman filter, the Kalman filter is an optimal fusion framework if everything is Gaussian zero noise. If it's not, you start seeing biases and the filter will drift away. Like for noise values, if the noise is not Gaussian, what will happen is, of course, that let's say you have constant noise, like it's really just a rectangle. Then the filter will assume still a Gaussian peak, so will actually update a lot more towards the value that it should. So since the Kalman filter is not sampling the shape of the noise, it will do the wrong correction. It will make the wrong decision how far it should correct the prediction towards the camera. how far to move away from the prediction. And this is also the reason why we will be talking about the Bayesian filter in the end, because Bayesian filter is something which allows you arbitrary probability shapes. It can be even a discontinuous function. So Bayes filter is something which can have a step function as p, and is still allowing you to do the correct fusion. Kalman filter is a special case of the Bayesian filter, which reduces the complexity of the calculation. To calculate the Bayesian filter, you really need to take into account the entire space in which you're operating, which takes a long time. And this is just because the filter needs to sample basically in the entire space what's happening. Kalman filter gets away with the simpler calculation just because it does not need to sample the shapes. It assumes they are Gaussian. And if the assumption is wrong, then the correction will be also not optimal. This was a wrong explanation, but I hope you get the point. I'm trying to read. I have a question concerning the Kalman game. Oh yeah, this is how it should be looking like here. So the question is exactly what I was already explaining before. Maybe it's already answered why there is this HPH transpose in the Kalman filter. The problem is the H matrix is basically something which transforms between the state space and the measurement space. And you cannot add two values if they are not in the same coordinate frame. So H is basically transforming the covariance into the coordinate frame of the measurement. And that's when you can do the addition. So that's why in the inverse is HPH transpose plus R. The HPH transpose is really just transforming the covariance into the measurement space, so you can add the R to it and do the inversion. But I talked about this when I was writing the equation, so I guess this is a question which came earlier and I just never noticed. So basically, I need to wrap up now because we have this Automatica today. I would really recommend you, if you have a chance, to listen to the talks. Today there are talks from experts all around the world in the Munich Eye channel. Maybe go to MSRM website and check if you can find the link. And I am also involved a little bit in this, so I need to go back to them. And I compensated now already my being late, I hope, by extending the answering questions a little bit. So what we need to do in the next is really extend the Kalman filter to SLAM and dealing now with the real world problems with nonlinear functions. And to go to the last questions, to the cases where the noise is not Gaussian, but maybe even a discontinuous function. This will be really important for global localization, because for global localization, the probability to be in different rooms may be just a step function for different spaces. You will see it on the slide. So I need to stop for today. I will put now the next slide set afterwards and add the link to the TUM exam, so you can see basically how to deal with this. And I will give, once the TUM exam account is created, I will also start this test exam. Don't get it wrong, the test exam is not test questions. The test exams are really just empty rectangles in a PDF file, which allow you to see how to download the PDF, how to deal with this at home, and how to upload it to make sure that your whole tool chain is giving the correct answer. So thanks for today and see you next week.